gonna go back to 0 hours 1 minute. Okay, and we're gonna do Umbriel and Oberon, and I hope this is not gonna be too quick as I hit the forward button. So Umbriel here. Yeah, I think I can manage that. Oops, a little bit more. There we go. So again, it started on January 1st, 2011, and it has completed one orbit January 5th, 3 in the morning. Go back one last time for Oberon. And here we go. Okay, and there it has to return. There we go. Just a little bit more. Okay, that one is January 14th, 11 in the morning. So now you got all the data to put in there and all the data to calculate that constant for each planet. And let me just show you here the sample data for Miranda. 1.41 squared divided by 130,000 cubed. Notice I changed the units. Earlier it was the diameter of the radius of the planet. Now I'm using kilometers. Could have used miles. I'm using kilometers. So the constant I come up with is actually really tiny, 9.049, and then 10 to the negative 16. That means that the decimal is shifted 16 times to the left, and you have all these zeros in between. But this is what you're going to write down: 9.049, and then I already put on top 10 to the negative 16, so you don't have to write that down again. And of course, for Umbriel and Oberon, you're supposed to come up with virtually the same thing. Okay, for the last part here, for the moon, you have to figure out, well, how long does the moon take to orbit Earth? Look it up. The distance from the moon, you also have to look up. Then you calculate that constant. And by the way, the distance you have to look up in kilometers. You calculate that constant. Again, notice that it's going to be really small. That's why you did that exercise for Uranus a moment ago, to see how you handle really small numbers. Okay, to show you then what's going to happen next year. So you have the period for the moon, the distance for the moon, you come up with this constant, and then here you have to figure out, well, a stationary satellite above Earth, any kind of satellite, has to obey the same Kepler's third law, which means it has to have the same constant. So whatever you come up with here, you have to write in here, and you have to figure out where you put that stationary constant. What kind of stationary satellite. What kind of satellite is that? Well, communication satellites, for example, they hover above the Atlantic to transmit television and radio programs, as well as telephone links between Europe and North America, for example. It could be above the Pacific between Asia and North America. In any case, they hover over there, and that means they have to orbit the Earth in just the same amount of time as the Earth is rotating. So 1 day, 24 hours. And you have to determine where do you put that satellite. You can't just put it anywhere. You have to put it at a certain distance, because if you put it too close, it will orbit too fast. If you put it too far, it orbits too slow. You can only put it at one particular distance, and Kepler's third law tells you where, because whatever constant you came up with here for the moon, that satellite has to obey that same constant, take on the same constant. Okay, let me give you an example. Let's assume that we came up with 1.316 10 to the negative 14 for that constant calculated from the moon. That would be the same constant for the stationary satellite. So that's the number you would use. Here you have to work backwards. So instead of squaring and cubing, what you have to do is you have to do the cube root. So let me show you that in order to figure out the distance. So you take the cube root, there it is. You take the period squared, so I'm going to do 1 squared, and then I divide by that constant, So I divide by 1.316, 10 to the negative 14, and I come up with 42,300 or 42,400 kilometers if I actually gave you the correct constant. And that would tell you that you can only put that satellite here at 42,000 kilometers, roughly 26,000 miles. If you put it closer, it will orbit too fast. If you put it further away, it will orbit too slow. Again, why is that important? Well, okay, this is, I think I made this quote like 10 years ago in my lab sheet. I'm sure this is like 1,000 or 2,000 or so. They all have to obey Kepler's laws, in this case Kepler's third law. One thing I didn't mention with Kepler's third law, one thing I didn't mention yet, is that the constant that we come up with from Kepler's third law includes the planet's mass, or the planet's mass for each of the moons, or in the case of the Sun, it includes the Sun's mass. It wasn't really important as we went through this exercise here. We didn't come across it, but it's included there. So here's my last question. The masses of Mercury, Venus, and Pluto were not accurately known until the 1970s. Why not? Okay. And that finishes this exercise.